right, we have first the circle, which is a set of all points that are equidistant from a given point called the center. Okay, we name a circle using the center point. So we draw a little picture, circle, and then we call it P, because that's the point that's in the middle. Okay, you know this. A radius is a segment that has one endpoint at the center of our circle and the other endpoint on the circle itself, on the outside edge. So can you name a couple of radii? AB, wait, AP did you say? So AP, BP, what's the last one? CP. Okay, those are all radii.
Is the first name it radii?
Huh?
Where it says name it?
Nope.
It doesn't say.
Just circle P.
It doesn't say name it.
Okay.
Where?
Where? Look at
Yeah, that's only on that one though, not on radio.
That's what you would
It
do.
says example.
Hey.
Are you still on video?
Yes.
It says example, not
Hey,
name.
can you stop?
Not wrong.
Okay, so a chord is a segment that has both endpoints on the circle. So what are the chords in this diagram? I see one that's BD or DB.
Cooper, sit down.
I can't see your big laptop.
What's the other one?
AB.
AB. Okay. All right, what about a diameter? Where's the diameter? AB. This is a chord that contains the center point of a circle. So all diameters are chords. Are all chords diameters? No. Okay, AB. Okay. So next thing is that there are infinite radii and diameters in a circle. So we can draw infinitely many radii out from the center of the circle to the edge of the circle. And we can draw infinitely many diameters at any angle. Okay, that's fine. All right, next, secant. A secant can be a line, a ray, or a segment. It has to intersect the circle at 2 points. So we're looking down at this picture right now. So on that picture, what are the secants? You see that it's going to be the A and C stuff? Okay, so it can be a line. So it can be the line that goes through points A and C, line AC. Okay, it says it can be a ray. So I can call it the ray AC can be a secant, or the ray CA. It says that it could also be a segment. So it could be segment AC. Any of those can be secants. All right, we're going to draw a Venn diagram. All right. This big box is a box full of secants. Okay, secants intersect the circle in 2 places. Write this down. This is going to help your brain. Okay, what else intersects a circle in 2 places from our list of vocab so far? What? Yeah, a chord. But chords are specifically segments. They are not lines, they are not rays. So some of our secants are going to be chords. Is this making sense to you guys? So inside of the big box of secants, some of our secants are chords. Okay, these are specifically segments. And they have endpoints on the circle. I should have put like a little dot in my circle up here. Would you add a dot? Thank you very much. All right. Now we said that all diameters are chords, but not all chords are diameters. So in the chord box, I want you to put the last box for diameters. A diameter is a segment with endpoints on the circle that passes through the center. I kind of ran out of room. So every diameter is a chord and a secant. Okay? Every chord is a secant. Are we clear how these kind of like fit together like little nesting dolls? Okay, perfect. All right, now we're going to talk about tangents. Tangents are lines, segments, or rays that intersect a circle at exactly one point. So looking at this picture, I can say line AB is a tangent line. The segment AB is tangent to the circle. I can say that either ray AB or ray BA is tangent to the circle. Okay, you are also going to need to know that the tangent line is perpendicular to the radius at the point of tangency. Do you see that that makes a right angle with the radius at that intersection point? Okay, so tangent line, it's an alternate spelling of tangent, is perpendicular to radius at point of tangency. Okay, obviously the point of tangency is where the circle and the tangent intersect. Cool.
Yeah.
All right. You guys are doing pretty good. We had a rough start, but it seems to be going better. All right. So for each of these, we are going to tell whether the line or segment is best described as a chord, a secant, a tangent, a diameter, or a radius. For the ones that are both, we are going to list all of the things they are and then like box the best answer. If I only give you one answer to put, like what would you put? Does that make sense? All right, what is HC? Radius. Okay, what about segment BE? Okay, it's a secant. It is also a chord. What is the most specific name for it? A chord. So we're going to box a chord because if I only give you the one answer option, that's what you would pick, but it is also a secant. Chord is the best answer because it is the most specific. All right, what about line DG? Tangent. All right, what about segment BH? Diameter, it is the most specific. Okay, but we also know that every single diameter is also a chord and a what? Yep. So if I'm giving you like a situation where you have to check all that apply, I'm expecting you to pick all three. If I'm just giving you like a fill in the blank where you can only say one option, then you pick diameter. Does everybody understand the expectation?
Yeah.
Okay, perfect. All right, AF. It's a secant. Okay, why can't it be a chord? Tell me about its endpoints. Are its endpoints on the circle? No. So if the endpoints are not on the circle, it can't be a chord. Everybody okay with that? All right. That one was a weird one. Flip. All right, it's time for the easiest problems in the world. Okay, first it's time for some stuff you already know. You do. You'll know it as soon as you'll recognize it as soon as I write it down. Okay, we've got two equations for the circumference of a circle. The first one is that circumference is equal to 2 pi times the radius, 2 pi r. You've seen that one, right? Yeah. All right, now we know that each diameter has 2 radii in it, right? So if I have a 2 and an r, what could I replace 2r with? Okay, a diameter is equal to 2 radii. So what can I replace 2 radii with? A diameter. I could also have it be c equals pi times the diameter, right? Because d equals 2 radii. Did you say the wrong thing with like the most confidence?
Yeah.
Awesome. All right. Well, I just appreciate you not leaving me hanging because that's embarrassing. All right. The area of the circle is all the two-dimensional space inside the circle. We all know that the area of a circle is pi times what? R squared. That's it. Okay, so for example 2, we have to find both the area and the circumference for this circle. So if they're telling us our diameter is 6, what is our radius? Woo, 3. Okay, so on these problems, they're going to probably give you either like one or the other, and you might have to like solve for the other one. You just either double the radius or chop the diameter in half. Got it? All right. So for the area, we're going to say pi times our radius, which is 3 squared. Okay. So that is 9 pi. What is this? Inches squared? Okay, notice that it says in terms of pi and rounded to the nearest tenth. So we can say that that is approximately, do you guys know how to put pi in the calculator? No.
There's a button.
There's a button. Okay, so 9. Do you guys see that if I hit the second button and then the power caret, I get pi? The power caret is right underneath clear. Okay, so I just put 9 pi in my calculator and hit enter. So what is that, 28.3 nearest tenth? 28.3 inches squared. All right, let's do the circumference. All right, since they gave us the diameter, let's use that one. So circumference equals pi times the diameter, which was 6. So In terms of pi, it would just be 6 pi inches. And then rounded to the nearest tenth, 6 pi. I'm getting 18.8. Easiest problems in the world. Okay, look at example 3. It's telling us the area, but the directions say that we have to find the circumference. What do we need in order to find the circumference? We need either the what or the what? The radius or the diameter. Okay? Doesn't the area of a circle have the radius in it? Okay, so I can take this area and solve for the radius and then plug it in to find my circumference. That's the plan. So I know that my area is 289 pi, and I know that the formula for the area of a circle is pi times the radius squared. Okay, now I don't want that pi hanging around. How do I get rid of pi on both sides of my equation? How do I undo multiplying by pi? Divide them away. Divide by pi, divide by pi. Pi is just a number like 4 or 5, except that it goes on forever without repeating after its decimal point. All right, now I'm left with 289 equals my radius squared. How do I undo squaring? Square root. I'm going to take the square root of both sides. Now, this quadratic equation has 2 possible answers, the positive root and the negative root. You have to list them both. So the principal root is the positive one, and then we also want its opposite. I think it's 17. Do we need to show how to do that on the calculator? Okay. On the calculator, to get square root, I go to second x squared. You see the little square root in blue? Okay. What is it, 289? Okay, notice that it only gives me the principal root. I have to know that it's also negative 17, right? Huh? What? Okay, negative 17 and positive 17 both satisfy this equation. Can a radius be negative? No. So I have to write down the negative one and then cross him out because he does not work in this situation. But I have to list that bugger in curly brackets because he satisfies my quadratic equation. Cool? I have to list them both and then cross out the one that doesn't work in the constraints of this scenario. All right, so my radius is 17. Let's plug it in. Circumference equals 2 pi times my radius. Okay, let's give our answers in exact form and rounded to the nearest hundredth. So in exact form, 2 times 17 is 34. That is 34 pi inches. Okay, and then I can put it in my calculator and round. 34 pi. I'm getting 106.81. Okay, in general, when you're performing calculations, you want to keep the pi in there as long as possible because anytime you start rounding, you're introducing a rounding error. And if you continue to perform calculations with that rounding error, your answer gets farther and farther and farther from the actual value. Does this make sense? Especially when you're start multiplying by really big numbers, right? Because that rounding error just gets magnified by several orders of magnitude. Okay. right, a central angle. A central angle is an angle whose vertex, that's where it bends, right? That's the middle point in the middle of the angle where it bends, is the center of the circle. So can you give me an example from the picture of a central angle? Angle. Okay. This one?
Yeah.
Right? So make sure you put the E in the middle. You can either call it Fed or DEF. Okay, there is a massive, massive, horrible typo right here. Okay, and if you ever put this on your paper, no, better not. Okay, it says congruent measures. We know that it's figures that are congruent. What are measures? No. If they're the same, measures are not congruent. They are equal. Okay? The central angle and the inscribed arc are different figures. How can they be congruent? Like, that doesn't even make sense. So you better not ever put that. I did not. I have yet to fix this, but I'm telling you now, you better not ever put this because we've talked about how figures are congruent, measures are equal. Okay, so what we know is that the measure of angle DEF is equal to the measure of this arc DF, to the measure of DF, the arc. Those figures can't be congruent because they are not the same thing. That's like saying a square is congruent to a circle. Like, it's not even possible.
What's that line?
Their areas can be equal. What?
What is that line?
That's an arc. What? It's an arc. We're going to talk about it in a second. All right, an inscribed angle is an angle whose vertex is on the circle and whose sides of the angle are both chords. Okay, so for an inscribed angle, all of my points are on the circle itself. Okay, so that would be angle A, C, B. Why can't I call that angle ABC?
Because the C is the bend.
The C is the bend, the C is the vertex.
Oh, yeah, good boy.
All right. All right, here we go, guys. Okay, a semicircle, half a circle. Okay, a semicircle is a special kind of arc that is exactly half of the circle. So what is the semicircle here? Yeah, so TS. Semicircles we have to name with 3 letters.
So
It's like a major, yeah, we're going to call it TRS. Okay, so TRS. Okay, if we have a cute little minor arc, we only have to do 2 letters. A minor arc is going to be less than half of a circle. So, for example, here's a little minor arc, RS. Okay, can you see another minor arc?
is it RT?
RT, I like it. All right. Okay, a major arc is going to be bigger than a semicircle, so more than half of the circle. So this also needs 3 letters. Okay, we need 3 letters.
STR.
Okay, STR is 1. Okay, don't forget to put the arc over the top of it. Okay, what's another one? RST is another one. It's a little bit smaller, but it's still bigger than half the circle.
TSR is another one.
I think that one's the same one.
No, how?
TSR, RST, that's the same one.
Oh my gosh.
Okay, any other ones we need to say?
Shut up, Robert.
Okay. All right. Do you guys remember what adjacent angles are?
But it says
Like ones
I
that
know.
like neighbor each other.
Yeah, they're neighbors. Okay, so adjacent angles share like a common side and a common endpoint, right? Okay, so they're like very neighborly. The important thing is that they do not overlap. So they do not overlap. They have exactly 1 point in common. Okay, I guess they overlap in like 1 point. So they only overlap in 1 point.
Not RPS
And RPT. Or no.
No, dude, you're stupid for the heck, no.
I didn't say that.
Okay, so
TR.
TR and
RS.
yeah.
Light work. Yeah, you're stupid.
So they only share point R. Other than that, they're not overlapping. Questions? Guys, we're doing pretty good.
Are we gonna get done with notes today?
We're gonna do example 4 and then we're gonna be done for today. All right, we're gonna identify the following in circle O. Minor arcs.
AD.
AD.
CE.
Ooh, that was a goofy looking arc. Okay, can we just go around? DE.
Oh, shut up, Cooper.
Okay. EC. Hey guys, it's getting a little wild.
And CA.
CA.
Good job, Anthony. Yeah, good job.
Okay, any others? All right, what about semicircles?
ACE.
Okay, ACE. Thank you for using 3 letters. I almost forgot. What else?
ADE.
ADE. Okay, are there 2 more?
Yeah.
What are they?
DEC.
DEC, yep.
And then ECA.
ECA, I agree. ECA. Oops. Ooh, I don't know. Quality control. I had a spasm. It's fine. Nobody saw it. It's just forever on the internet, immortalized. It's fine. Okay, major arcs that contain point A. Okay, I'm saying DAC.
Yeah.
Anything else?
Wait, what are we?
I thought DAC is the same.
Oh, you're right.
Yeah, what are you talking about?
All right, what about
DAE.
DAE? Okay, I like that better. Someone was paying attention, not me. I'm like ready to get out of here. What else?
AA.
AA.
Okay, it doesn't have to be in the middle.
EA.
A doesn't have to be. What was that?
Never mind, that's the same thing.
CEA. Yeah. All right. What about ADC? Oh, ACD is one. And ADC is one. Okay, do we see any other ones?
No.
Okay, thank God. All right, adjacent arcs.
ACCE.
It's kind of like the minor arcs and then some of the semicircles, right?
CE.
All right, give yourself lots of room for this. AD.
Oh my.
I don't know that we have to list them all.
So we're most time listening.
Okay, AD and DE.
Yeah.
All right, what else? Can I have a major and a minor? Let's do an example like that. All right, how about ADC? Oh,
ACCE.
huh?
ACCE.
ACC.
Okay, so I think in the definition it said that they could only share 1 point, so I don't think we can do like the semicircle that I was thinking of.
Yeah, ACCE.
A, C, and CE, yeah. Okay. Let's not call each other that.
Yeah, Anthony, come on, dude, watch me. Yeah. What?
All right, I'm tempted to send this video to your parents.
Whoa. Whoa now.
Yeah.
I didn't even do that.
Okay, keep telling yourself.
Well, you can send them the part.
All right,
where I
do
was
we
obviously
see any
right.
others? What about DE and EC?
Yeah, she was sending me that part. Because she knows I was right. So do you, Anthony. You also know.
Will you please stop? All right, so there might be more.
Oh, boy.
Jeez. Where did we get all those from?
All right, we're gonna stop it there. We're gonna